solids have strong forces between particles, so they don't move much, they just vibrate around. In a liquid, they have weaker forces, so they can move around a bit, but they have similar distance to liquid because they can't really compress. And gases have very weak forces between molecules, and you can usually just assume that they're not there. The temperature of something, measured in Kelvin, is proportional to the average random kinetic energy of the molecules. So if you just take some random molecule and average them all out, then the kinetic energy of the average of all of them is proportional to the temperature. So this kinetic energy is equal to 3/2 kBT, which is in the formula booklet. And make sure you don't use Celsius because that is negatives and that would not work. The specific heat capacity is the energy required to increase the temperature of something by 1 Kelvin. And you can put this in a formula by this one, which is given in the formula booklet. And only use this when something is changing temperature and not phase. For that, you can use specific latent heat, which is the energy required to change something phase, and it's equal to mL. But this is the specific latent heat. This is just the heat energy given. And only use this when something is changing phase and the temperature is constant. And the latent heat of fusion is for melting, and the latent heat of vaporization is liquid to gas like a water vaporizing. Also, know about those heating and cooling graphs and stuff. And yeah, know what the flat seconds are. Yeah. So, you know that the power is equal to 2200 watts. And power is equal to work over change in time. And here we're trying to find the change in time. And we know work is the change in energy, which is the same as Q in our formulas. And here, Q is equal to mc delta T. In the exam, you'll get the C of anything, but it's water, which is 4200. Don't remember that though. And 0.9 times 4200 times 75 is equal to 283,500 joules. So now you can put this into this power formula, so change in time, to work over power, which is equal to 283,500 over 2200, which is equal to 128.86 or 130 seconds. So for the second part of the question, now we're trying to calculate the power, and we know the time. So we just know power is equal to work over the change in time, and the work is the same. So take that from your last calculator, 283,500, divide that by 150 seconds, and this is equal to 1890. So this is the power that went in. But the power that transferred to the surroundings is the original power, 2200, minus this thing, which is equal to 310 watts. Thermal energy is heat, and when two things touch each other, then thermal energy will be transferred from hot to cold, and when they're the same temperature, they're in thermal equilibrium. Because of forces in a solid, work has to be done to overcome, and breaking bonds requires energy. But the intermolecular potential energy is the energy that could be released if these bonds are broken, which releases energy. And gases have low forces between them, so most of their internal energy is kinetic. And the internal energy of a substance is called U, and it's equal to the kinetic energy of the particles plus the intermolecular potential energy of the particles. And temperature is not the same as internal energy unless it's an ideal gas. And temperature is constant when something is changing phase because only intermolecular potential energy is increasing. So thermal energy transfer can happen in three ways: conduction, convection, and thermal radiation. Conduction. So thermal and electrical conduction are similar and happens without a large-scale movement of atoms in a solid. So if this is the atoms in a solid, then they don't really move when conduction is happening. They just, let's say this side is hot and this side is cold, then these atoms on this side are vibrating faster than on this side. And these transfer energy to free electrons that are in the metal. So now there's super quick free electrons on this side, and that transfers some energy, and these fast free electrons redistribute the energy along the rod to the cold side. And these ions with less energy on the cold side gain energy until the whole rod is the same temperature. This can also happen in a gas and liquid, but atomic connections are weaker, so vibrations do less and it's usually negligible. And you usually shouldn't say this on an exam if you have to talk about heat changing in a liquid. And this is the only one out of the three with the formula, which is called the thermal conductivity, which is a measure of how good something is at conducting thermal energy in a steady state, which means that the temperature at any point doesn't change. So you can see this in the formula booklet, where K is thermal conductivity. And delta Q over delta T is the rate of energy transfer. And you should know this is the same as power. So remember in the formula, this delta X. So let's just say you have some cylinder here that you're finding the rate of energy transfer across. Delta X is this thing here. The area of this thing is the area in the formula. So here you often get circles, which is pi r squared. And the temperature change is the difference in temperature between the two ends. So if this side is at 0 degrees Celsius and this is at 30 degrees Celsius, then this is 30. So to do this question here, you just write out what you have. Delta T is equal to 300. Delta X is equal to 0.6 meters. And the area is equal to 0.01 squared times pi, because it gives you the diameter. Don't forget about that. And if you put this in your formula for this, you will get 37.699 watts. So that's the answer for A. So to calculate the mass of ice that melts in a minute, you have to use Q is equal to mL. There's a few ways you could do this. You could times this by time, but I'll just divide both sides by the change in time. And we know the rate of energy transfer is this thing right here. So 37.699 is equal to M. And in this case, it doesn't give you L here, but it implies you know it. But on the exam, you do not need to know it. And it is 334 for ice. And you're dividing this by 60 seconds because it's happening in a minute. And if you just put this in your calculator, you will get M is equal to 6.77, or is equal to 6.8 kilograms. So convection is the movement of a group of particles in fluids because of the density changes. And this happens in macroscopic ways instead of microscopic, like conduction, which means that you can actually see it. Because in conduction, it is the molecules vibrating. Now it's the liquid actually moving. And this can't happen in solids because the particles can't move around like that. For example, when water is heated by something like a stove or something, then it has an upward force because the particles move further apart here because their average kinetic energy is higher, which gives it an upward force. And these particles move up here, but now the density is lower down here. So the colder air is pulled into here, and then it gets heated up. So then you get like a circle that looks kind of like this, with the air moving around like this. So if there's a pot getting heated, then eventually all the water is going to get hot. And you don't need to know any formulas, just know the theory. So for thermal radiation, it's energy transfer because of electromagnetic radiation, and this does not need a medium and travels as a wave. And you will learn more about this in C2 and all of C really, so that's later. So you do need to know more about thermal radiation, like a black body radiator absorbs everything and emits everything. So all the light that comes in is absorbed and emitted. You also need to know intensity is equal to power over area, which is in the formula booklet, and that all wavelengths are emitted by a black body, and this depends on the temperature, as shown by this graph. You don't need to know these exact numbers, just relative to each other, and make sure that the graph does not go through the origin, because a wavelength is never equal to 0. So this image shows that as temperature increases, then for each wavelength, the intensity increases. So for every single wavelength, the higher temperature will have more intensity of that wavelength, and that the total power increases, power per square meter, and that the curves skew towards shorter wavelengths, which are the higher frequencies, and that the peak of the curve moves towards shorter wavelengths. And like that, I mean that it goes more to the left. The peak goes more to the left. You also need to know about Wien's displacement law, which says that the height and the shape of the curves depends only on temperature, and that the maximum wavelength times the temperature is equal to B, which is in the formula booklet, and is a constant. And the max wavelength is when intensity is at a max. You also need to know about the Stefan-Boltzmann law, and it's a power radiated from a black body, which is also related to temperature. Remember that luminosity is always the same as power, which is energy per time. And here it's equal to this thing times A times T to the 4, where this thing is just another constant in the book, and A is the total surface area of the black body. So if it's a sphere, and for a sphere, the total surface area is 4 pi r squared. So for this question, if you think about a plate with some surface area, then it emits some power, but it also takes some power from the environment, and we need to consider that. So the net power is equal to the power out minus the power in, because they're going in different directions. So the net power is 50, which is equal to this times the area times the temperature to the 4, minus this times the area times the surroundings, which is 20C, which is 293 Kelvin to the 4. Now, rearranging this for T to the 4, it's equal to 50 plus this 0.025 293 to the 4th over 0.025 times this thing, and you will get the T is equal to 454 K, or about 181 degrees C, and you should round that in your final answer, obviously. So for player B, it's kind of the same thing. The additional power, P, is equal to the power out minus the power in. And we can just shorten the formula from before and change it to 2 to the 4 minus 2 3 to the 4. And T now is 200C, or which is the same as 473 Kelvin. And if you put that in your calculator, you'll get 60.5 something. So the additional power is 60.5 minus 4, which was 50, is equal to 10.5. And this is in watts. And this is the same as 11 if you round. Intensity is equal to power over area, like before. So intensity, using the formula we just got, is power divided by 4 pi T squared. If the area, so this is for a sphere, because this is the surface area of a sphere. So the intensity is how bright something appears, which is called apparent brightness. Power is stellar luminosity. So, and T is the distance away from the star in this case. And the apparent brightness is what we see from a telescope on Earth. So I'll just add some of B.2 as well. So approximations of black bodies are called gray bodies, which emit less energy per second, which is power, than a black body at the same temperature. And you can tell how gray something is by the formulas of B.2. For example, the emissivity formula is the power emitted by this gray object. So what actually happens with the power that would be emitted by some black body. And when radiating object is a black body, or is closer, then the emissivity is closer to 1. And the solar constant, if you ever see that, is the intensity of the sun at Earth. And you can use the same formula, B is equal to L over 4 pi D squared. But this intensity is for 1 square meter on the Earth. But really, if you think about the Earth and the sun, then it's putting its brightness on an area of pi r squared. So that's what the energy is coming through. So as intensity is equal to power over area, then the power is S times pi r squared divided by the area of 4 pi r squared, so equal to S over 4. So the intensity at any point on the surface of Earth is S over 4. So if you're calculating the intensity at a point on the surface, divide your value for the luminosity you find, not the luminosity, divide your value for the brightness, or the apparent brightness you find, by 4 for a point on the surface. So just remember, if the question says at any point on the surface, you have to divide your value by 4. And this occurs for any planet, not just the Earth. So if you got Mars or something, then divide by 4. And albedo is like emissivity. It's the amount of energy scattered away, just showing how bright it is. So it's also in the formula booklet. But remember, the energy scattered by a black body is the same as what's incident on it. So if something scatters all the light away, then it's going to be white. power has to go somewhere. And the emissivity is like the opposite of albedo because of it's what it sucks in. So E is equal to 1 minus A, and you should know how to do it. You also do need to know about the greenhouse effect when gases in Earth's atmosphere trap energy and rise up to the Earth's temperature. And these are mainly CO2, H2O, like water vapor, methane, which is CH4, and nitrous oxide, which is N2O. And it happens a bit naturally, but the enhanced greenhouse effect is what humans do, and this is not good for the environment. So you can read the rest of this if you want, and just about greenhouse gases and why it happens. You do need to know this as well.